Alright, so welcome to how to solve projectiles when given an initial angle. Okay, now previously to this, you guys have only seen problems where we have an initial velocity at the horizontal or with only an x velocity component, no y. Those are simple to solve for because they don't involve, like I said, an initial velocity in the y, which will take us to a quadratic. So we're going to go over what that looks like and talk a little bit more about that. So here's a great example problem of that. So we're at a 25-meter cliff. Okay, so our delta y here is going to be 25 meters all said and done. We start here, ball's going to go up, or whatever object we're throwing, and it's going to come down and land on the ground 25 meters below. Okay, initial velocity is 10 meters per second at an angle. Now our trig's going to come back, okay, because again, we can't do anything at a 30-degree angle. We don't have the math to do that. We need to put everything on an x and a y component. So here's your velocity in the x, here's your velocity in the y. Okay, again, back to our trig functions. If I want to solve for my opposite, okay, velocity in the y, I'm going to need to use sine. So sine of 30 is going to be equal to my velocity in the y over 10 meters per second. That ends up being 5 meters per second. Okay, velocity in the x, similar, but we go cosine of our angle, which is equal to velocity in the x over 10 meters per second. Our velocity in the x ends up being 8.7 meters per second. Okay, so we have our x and our y components here. We'll just label those again. So this is our v, y. Notice that it's positive because, again, that way and this way. So our velocity in the y is a positive number. Velocity in the x also positive. Okay, so that's essentially what we know. So if I'm going to make my know and want column, okay, I know that my vi in the x, or my vx, is 8.7 meters per second. I know my vy is going to be 5 meters per second, and that's my initial velocity again. Okay, I know my delta y, it's going to drop 25 meters, all said and done. Okay, what we want is the range, okay, or the delta x. Now, when we solve for that, okay, same strategies are other problems where there's no initial angle. We need to figure out how long this ball or this object that's being thrown is going to be in the air. Okay, and the way that we can do that a number of ways. We can either use our range equation. You guys remember our v average in the x, okay, is equal to delta x over delta t. But we don't know this, so we can't use that right now. So the one that we're going to have to use is our delta y is vi or vy t plus 1/2 at squared. Okay, so let's use that, and I'm going to go ahead and do my work down here now to find the time. So before we can find the range, we need time first. So solving for that, we said we need the delta y equation is equal to vy t plus 1/2 at squared. Now acceleration is gravity, our vy we solved, our delta y we're given. Okay, I'm going to go ahead and unplug my numbers in. 25 meters, we're going to drop in our delta y like we said, but again, remember we're starting up and we're moving downward. That's a negative 25 meters. My vy, we solve for it to be positive 5 meters per second times t plus 1/2 times my acceleration, negative 9.8, because again, objects accelerate towards the center of the earth, t squared. Okay, now again, this is a quadratic. We cannot solve for this unless we do a quadratic. So just as a review for you guys, again, quadratic format is 0 equals ax squared plus bx plus c. Now realistically speaking, instead of x's we have t's, but we're going to solve for t's. Okay, so I'm going to rearrange my equation so that I have it in that format. Okay, because ultimately I want to plug it into this equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we're going to plug it in, or we're going to rearrange first and then input so we can get a time. Okay, I want to get 0 on this side, so I'm going to go ahead and I'm going to add 25 to both sides. So I get 0 is equal to 5t, like I have above, plus 1/2 times negative 9.8 is negative 4.9 t squared, and then add 25 to both sides, that drops, plus 25. Okay, so I have my format, just need to rearrange t squared, t, and 25. So 0 is equal to ax squared, so negative 4.9 t squared plus 5t plus 25. This is my a value, this is my b value, there's my c value. So let's take that, put it into our quadratic. I need more paper here. I'm going to plug that into my quadratic. Okay, so negative b, we're going to have negative 5 plus or minus the square root of 5 squared minus 4 times my a value, negative 4.9, plus my times my c value, 25. All of that over 2 times my a value, negative 4.9. Okay, now I will tell you, just seeing a lot of you guys work through these types of problems, we make mistakes not inputting the values in the data here, but we make mistakes by trying to crunch everything all at once. My suggestion to you is to just solve this, multiply that, and do it slowly in steps. And I'll show you what I mean. Okay, so again, we're solving for time. So t is equal to negative 5 plus or minus. Okay, that's 25, so the square root of 25 minus negative, that's actually going to end up being plus, okay, 4 times 4.9 times 25. I'm going to crunch it real quick. So we get plus 490 here, all over negative 9.8. Okay. Simplify further, 490 plus 25. So we get negative 5 plus or minus the square root of 515 all over negative 9.8. I end up with negative 5 plus or minus 22.7, rounding to 1 decimal, all over negative 9.8. Okay, again, oops, I forgot I wasn't showing that. So again, this is what I did, and I was doing the math off, sorry. But we simplified slowly. So negative 5, I crunched that to 25, I crunched these to 490, combine those yet, okay, and still further on until we have just simple numbers. Okay, now we can't have a negative time, there's no such thing. So right away I'm looking at this. If I add these together, I'm going to have a positive number on top, negative number on bottom. Can't have a negative time. Okay, so instead I'm going to go ahead and take negative 5 minus negative 22, or minus 22, divided by 9.8. That's going to get me 2.8 seconds. Okay, so now I have the amount of time the object's going to be in the air using a quadratic. So here it is. Now I'm going to go back to my no column, and I know that my time is equal to 2.8 seconds. I want to find my range now. I have the information to do so. We know that the object will be in the air for 2.8 seconds. We know the initial velocity of the object from up here is going to be 8.7 meters per second. Okay, and we have our range equation that we previously couldn't use. Now we can. We have a time. Okay, so our range equation again, okay, if you remember, is average velocity in the x, because this is a constant velocity, does not change. That's going to be equal to my delta x over delta t, or my time that it's in the air. Now, just again, rearranging, let's multiply both sides by time to get delta x by itself. The distance, or the delta x, the range, is going to be equal to this velocity in the x times our time. So I'm going to go ahead and do that. The velocity in the x we solved for before to be 8.7 times our time, which we solved for down here to be 2.8, and that ends up being 8.7, 24.4 meters. Okay, so that's how we will solve for these types of problems when we have an initial angle. Okay, again, just repeating strategy. We need to figure out first how far or how long the object will be in the air. From that, then we'll take our x and our y velocity components, okay, to figure out how far it's gone. Typically, to figure out how long it's in the air, you need to take the distance that it's going to travel, include the initial velocity in the y direction because both of these are y, and use that information to solve for time. If you have an initial velocity in the y, you are going to have to use a quadratic. From there, then, solve for time, and then go to your range equation, and after you have the components you need, you can solve for the range or the distance it's going to travel. That is solving for range, or solving the distance a projectile will travel given an initial angle.